Hello viewers, in today's session we are going to discuss an important limit representation of the famous Dirac delta function, right? So in this lecture we'll show that the Dirac delta function can be represented by this limit, that is limit L tends to infinity sine Lx over pi x, right? So viewers, we have already discussed some representation of Dirac delta function in our earlier videos, and in this class we'll see how we can represent the delta function as this limit using the concept of Fourier transforms, right? So let us first quickly see the Fourier transform of delta function and the inverse Fourier transform of delta function, right? Because we can arrive at this result by utilizing the concept of Fourier transform and inverse Fourier transform. So let us start. Now let us consider a function, say f of x, right? So the Fourier transform of this function f of x is denoted by f of k, and this is defined by this integral, that is minus infinity to infinity. Here we have f of x and e raised to minus I k x dx, right? So this is the definition of the Fourier transform of f of x, right? So now the first step to get this result is to assume f of x as delta function, right? So here I will take f of x as delta of x. So the Fourier transform of delta function is now given by f of k, and here we have f of capital F of delta x, and here we have minus infinity to infinity, and for this f of x now we can replace it by the delta function, right? So we have delta of x e raised to minus I k x dx, right? Okay, now here it is interesting to note that we have to evaluate this integral, and this integral can easily be evaluated by using the definition of delta function, right? So this integral can also be written like this: minus infinity to infinity. We can take this function in front of the delta function, so we have e raised to minus I k x, and then we have delta of x, right? So delta of x can be written as delta of x minus 0 dx, right? So now we can take this function, that is the exponential function, as g of x, right? So now to evaluate this integral, we'll make use of this definition, that is minus infinity to infinity. And if we have some function g of x which is associated with the delta function, that is delta of x minus a dx, then the value of this integral is equal to the value of this function at this point, that is x is equal to a, right? So we have g of a. So now using this concept, we can evaluate this integral. So here we have the value of a as 0, and the function is g of x, that is e raised to minus I k x, where I is the iota, I square is equal to minus 1, right? So the value of this integral is g of 0, right? And we can obtain g of 0 by taking x is equal to 0 in this function, that is e raised to minus I k x. So we have e raised to minus I k times 0, so we have e raised to 0, that is equal to 1, right? So now we conclude that the Fourier transform of the delta function is equal to 1, right? So we can write this result over here. So f of k, f of k, this is the Fourier transform of delta x, and this is f of delta x, that is equal to 1, right? Okay, so now let us find out the inverse Fourier transform of the delta function. So now to get the inverse Fourier transform of f of x, we can use this definition. So we can now write f of x as equal to the inverse Fourier transform of f of x, that is f of k here. So using this definition, we have 1 over 2 pi, and this is minus infinity to infinity, and here we have f of k instead of f of x, and here we have e raised to I k x dk, right? So this is the definition of the inverse Fourier transform, and this is the definition of the infinite Fourier transform, right? So now let us replace this f of x by delta x, right? So in this expression, we'll take f of x as delta of x. Then we have f inverse, and here we have f of k, right? And f of k is equal to 1. So we'll simply write here f of k. And here we have the coefficient, that is 1 over 2 pi, and then we have minus infinity to infinity and f of k, right? So f of k is equal to 1. So here we'll write 1, and here we have e raised to I k x, and here we have dk, right? So now this expression can also be written as a delta function, and then we have 1 over 2 pi. Delta x is equal to 1 over 2 pi, and here we have minus infinity to infinity, and here we have e raised to I k x, and here we have dk, right? So this is also a very important representation of the Dirac delta function, right? So delta x is equal to 1 over 2 pi, and the integral from minus infinity to infinity e raised to I k x and dk, right? So let us quickly see what we have done so far. We have to show that delta function, that is delta of x, is equal to this limit, right? So we have started from the definition of the Fourier transform. Then we have obtained the Fourier transform of the delta function by this definition, and we got f of k, that is the Fourier transform of delta x, is 1. And then we utilized the definition of inverse Fourier transform, and the inverse Fourier transform of delta x is given by this expression. So here f of k is 1, and so we have obtained the expression for delta x as 1 over 2 pi, and the integral minus infinity to infinity e raised to I k x dk, right? So now we'll move further by using this important representation of delta function. So now let us introduce the quantity L in this expression. That is, we can write delta of x is equal to 1 over 2 pi, and this integral can be written as limit L tends to infinity, and we can now write the lower limit and the upper limit as minus L to L, and here we have e raised to I k x, and here we have dk, right? So we can rewrite, or we can represent this expression like this by introducing the limit concept or the limit notation here. So we have introduced a quantity L such that this expression is equal to this one, right? So this expression and this expression are equivalent. So we have written limit L tends to infinity, and here the lower and the upper limits are respectively minus L and L. So now let us find out the integral of e raised to minus I k x with respect to k, right? So we know that the integral, that is e raised to mx, is given by e raised to mx over m. So utilizing this result, we can now write here 1 over 2 pi, and then we have limit L tends to infinity, and here we have the integral of e raised to I k x as e raised to I k x, and in the denominator we can now write simply ix, and here we have the limits minus L to L. So now to simplify this expression, we can write 1 over 2 pi, and here we have limit L tends to infinity, and we have 1 over ix, and first we'll take the upper limit. So we have e raised to I, that is ilx, then we have e raised to minus ilx, right? So taking k is equal to minus L to k is equal to L, right? So now here we have this expression, and this expression can be replaced by using an important identity from complex numbers. So from complex numbers, we know that e raised to I theta minus e raised to minus I theta is equal to 2I sine theta, right? So this identity can be obtained by the Euler's formula, which says that e raised to I theta is cos theta plus iota sine theta, right? So here we have e raised to ilx minus e raised to minus ilx. So the value of theta is equal to lx, right? So using this result, we can now write the delta function as delta of x is equal to 1 over 2 pi limit L tends to infinity, and here we have 2I sine. For theta, we can now write Lx, right? And in the denominator, we have I times x. So now we can write this expression as delta x, and we have limit L tends to infinity. Here we have 1 over 2 pi, and then we have 2I sine Lx divided by Ix, right? Now this 2 and this 2 get cancelled, this I and this I get cancelled. So we are now left with delta x is equal to limit L tends to infinity, and we have sine Lx over pi x, right? So multiplying these two together, we have pi x, right? So this is our required representation of the delta function in terms of limit L tends to infinity sine Lx over pi x. So viewers, this is how we can represent the delta function in terms of the limit L tends to infinity sine Lx over pi x, right? So here it is important to note that if we introduce new quantities, say epsilon, and epsilon is such that L is equal to 1 over epsilon, and when this L tends to infinity, then this epsilon tends to 0, right? So replacing this L by epsilon, we can also rewrite this representation of delta function as delta of x, and here we have limit epsilon tends to 0, and we have sine. For L we can write 1 over epsilon, so we have x over epsilon, and here we have pi x, right? So this is another representation of the Dirac delta function, right?